I'm going to talk about two projects today. One of them is done already. It's with Marta Serra Garcia, also from UCSD. Both projects are with her, and the first one is published already, like I said. The second one is now, we're still working on it, so any comments will be very appreciated. So we know that communication is important. It's important between people. It's important between other animals. And we don't know enough about lying, I think. Despite of the fact that there is so much literature about it, there are many puzzles that are still there, at least to me. One of them is why people don't lie more, right? So that's something that I still don't understand. But that's not what I'm going to talk about today. Today I'm going to talk about detecting lies. How good are we? What do we feel about how good we are? And how can we actually improve detecting lies? The first project, like I said, is published already, and we ask four main questions in it. Are people able to detect lies? The answer will be not really. Are they overconfident? Yes, they are. Are lies shared more often than truth? I'll try to, it's not maybe clear to you what I mean by that, but the answer will be yes. And how does sharing affect beliefs? It affects them in the wrong direction. Right, so that's what I'm going to show. So all bad news, more or less. Let's start with the task that they have. By the way, I'm not going to give you all the details of the experiment, so if you have any questions, please ask, but I'm trying to give you the bigger picture without the details, because I think it's more interesting. So we have two players, the sender-receiver game in the first one. The sender is sitting in the lab and watches two computer screens. In one case, he or she watches a real title and a picture from the New York Times. In the other case, they watch a blank screen. So each subject sees one real picture, one blank screen, and their job is to describe what they see if they see a picture, and make up a story when they see a blank screen. They are being paid if they convince the receiver, that we'll see in a minute, that they are telling the truth for each video. So receivers are going to watch the videos one after the other, have to decide whether it's true or false. If they decide that it's true, the sender is getting paid, otherwise not. So when I see a picture, I need to be as convincing as I can, because I want you to believe me, and when I see a blank screen, I need to lie to you in a convincing way. Okay, so that's the task that the sender had to do. Here's an example. So that's Becky, one of our graduate students. Let's hope that you can hear her. Okay, that's the 30-second that she had. True or false? What do you think? False. Okay, let's see the second one. True or false? No, one of them is true, one of them is false. So it's hard, right? It's a hard task. That was the actual picture, so it was the first one that was true. But you could see that it's, I'm sorry that the quality of picture is not that great, but you could see that it's a hard task, right? You are trying to guess something, and of course I chose one that is maybe a bit harder than others to do, but it's hard. By the way we made sure that we are choosing pictures randomly, so I use this exercise in my class, and in my class I choose pictures that are very hard to detect, because I want to convince the student in the negotiation class that they are bad at detecting lies. So I cheat, right? I choose pictures that are very hard to describe. In order to avoid this over here, what we did is we agreed that we're going to take all the pictures from the international edition of the New York Times exactly 6 months before we ran the first session. And we decided that before we knew when the first session will be. So there is no, we didn't select the pictures in a sense, they were selected randomly. The receiver knows about the incentives of the sender. they watch the videos, and then they have to decide, for each video, they have to guess whether it's true or false. And they're doing a few of them in a sequence. So we have 3 experiments. I'm not going to talk about all of them. In the first one, the receiver watches 20 videos. After each video, he or she has to say whether it's true or false. In the second one, so someone told us, well, 20 videos are not enough, so we created 84 more videos, and we had people watch only 8 videos, but the idea is very similar. And the last one will be about sharing. I'll get to it later. MTurk was done, some of it at least was done during the pandemic. Everything was pre-registered. First of all, how good are people at guessing whether it's true or false? That would be the theoretical distribution if we just toss a coin. That's what we should get. And that's how good people were, right? 50.6%. Basically, they're not better than a coin toss. They put a lot of effort into it. You could see that they wait, they watch it. They are just not good at it. And there is a similar fraction of type 1 and type 2, so believing something that you shouldn't and not believing something that you should, which is interesting, but I'm not going to get too much into it. That was the first result. So people, like I told you, are not good at detecting lying. That's, by the way, is not an original result by any, psychologists are talking about it for a very long time. The experiments are usually less nice than what we like to see. So for example, the people don't lie. So over here, we didn't tell people you need to lie. We gave them incentives to lie. So when they saw a blank screen, they could just say, oh, I see a blank screen, and then they wouldn't get paid. But they chose to lie because of the incentives that they got, right? So we did it a bit nicer maybe than psychologists do, but the results are there in psychology for sure. The second result is about overconfidence. So you can think about overestimations. That would be, I would think that I solved 14 when I actually solved only 8. Yes. So overconfidence in absolute terms would mean that I think that I solved more. In relative terms would be relative to the other people in the group. We ask them in which quartile they are. First of all, about the ability, we don't see gender differences. I'll tell you why I'm talking about gender differences in a second. You see that the numbers over here are a bit higher than the 50.6, but that's because, like I told you, I'm mixing experiments. But that's basically no gender difference in the ability to detect lies, to guess whether it's true or false. But both are overconfident about their ability, and men are significantly more overconfident than women about their ability to solve this, right? So there is, you can think about the argument that you can say, why should women be better at detecting lies? Because presumably women are better at understanding emotions and reading emotions, but we didn't find that over here. We found that men and women are overconfident, men are more. When we look at relative overconfidence, so those are quartiles, it should have been 25% in each quartile. What we see is that almost no one thinks that they are at the worst quartile, right? So no one says, I was the worst out of everyone. Actually, 25% say that they are at the top one, which 25 is right. I'll show you in a second that it's not necessarily the right people. And the vast majority of people are, well, I'm not great at this, but I'm better than average, right? The second quartile. So that's a result that we got in other experiments, by the way, and I think it's interesting that if you ask me about a task that I don't think that so if you ask me about speaking Hebrew, I would say that I'm in the top quartile over here. If you ask me about many other things, I would say, if they're important for me, I would say, well, I'm probably not at the top quartile, I'm in the second quartile. Very few people think that they are the worst, and also the second worst. Again, gender difference over here. I told you that that the fact that there are 25% of the people that think that they are in the top quartile says nothing, and the reason is that basically there is no correlation between what you guess, where you guessed you are, and where you actually were, right? So whether you were good, bad, that's as flat as it gets, I think. So people are not good. So people are really bad at this task. Those that are good don't know that they are good. Those that are bad don't know that they are bad. It's really all over the place. So now we're moving to sharing, right? So the overconfidence is also not a new finding. In many cases we see overconfidence, in many cases we see gender differences in this. Now we are moving to, I think again that we did it in a nicer way, but that's because of my taste maybe. Now we are moving to sharing. Now we are moving to something that I think we didn't see in the literature. So the first question that we wanted to ask is, are false videos shared more often? So you can think about fake news. And the usual explanation that we have for fake news is that we have motivated beliefs, right? So I see something about guns, and if I'm pro-gun control, I believe it, if it's against whatever, you see where I'm going, right? Motivated beliefs could really explain why we see fake news, but we argued that that's not the whole story. There are other issues with it. And what we're going to look at is, are false stories more interesting in a sense, and because of that, they're more likely to be shared, right? So that's what basically we're going to look at this, and then we're going to see whether this sharing actually affects how much we believe the video. So now we're going to have two receivers. We have 80 videos, or the 84 videos in this case, but less important. This person sees 8 videos, and after doing the task that we did before, guessing whether it's true or false, this person is also asked to choose one video to share with the second receiver. Okay, and I'll tell you in a second what does it mean. And this person, this R1, is paid if R2 is going to choose to actually watch this video. R2 will have options, and if R2 will choose to watch this video and the video is true, then this person will be paid, will get the bonus. Okay, so when I choose what to share, I need to choose something that is interesting, that I think that you'll find interesting, and that I think it's true. Okay, then come the second receiver. The second receiver watches only one, just a short description of each video that we made, so not the real picture that they saw, but we watched the video and our research assistant wrote a short description of it. And then receiver 2 also learned what was the decision of receiver 1, which one he or she wanted to share with them. Then chose 4 videos and assessed the 4 videos. So if the video that R1 chose to share is one of the 4 videos that R2 actually chose to watch, and the video was true, R1 get paid. So basically, I choose what to share with you, and I'll be paid if you choose to watch it and it's true. And what do we find? We find that lies are more likely to be shared. So 62% of the videos that were shared were actually lies, despite of the fact that my incentive was to choose videos that are true. Right? Yet I chose, usually I was as good as coin toss, now I'm actually worse when I choose it. 62% and we also see that if a video was shared, the second receiver was much more likely to actually watch it, 75.5% instead of 50% if it was random. So when I choose to share, I'm more likely to share a false video with you, and you're more likely to watch that video if I decided to share it, right? As a result, when sharing is allowed, we see much more, we see beliefs that are much worse than 50%. In fact, the only thing that I can tell you that you can take that is useful from here, if you'll ever participate in this experiment, is that if someone chose to share a video with you, don't watch this video, or you can watch it and say that it's false, actually. Sorry, you should watch it and say that it's false, right? Don't believe the video. That's the only useful takeaway out of it. Hopefully there are some others. Okay, they're just repeating limited ability to detect lies, overconfidence. Lies are shared more. Shared videos are more likely to be believed. Now we're going to move into the second part, which is the main thing that I want to talk about today, which is a follow-up paper that we did. And in this one, we used machine learning to help us. I'm not going to talk at all about the machine learning, so if that's why you're here, it's time, you can go. I'm just going to say what happened, because I'm not going to talk about the technology. 3 questions over here. Are people bad at detecting lies? Yes, people are bad at detecting lies. We saw it before. Can we come up with an algorithm that will be better than people? The answer will be, of course, we can, right? Otherwise, what's the use of machine learning? But the main question that we're going to discuss is, how can we use the feedback from machine learning, from the algorithm, in order to improve people's prediction, right? That's going to be the main thing that we are interested in. Golden balls, many of you saw videos from that, right? It's a funny show. It was a British show in which the last stage was a prisoner's dilemma. So the 2 final contestants reached the final stage. Usually they had lots of money, so tens of thousands of pounds in many cases. And it was a prisoner's dilemma. If both of them chose to split, they shared the pie. So say that the pie is 10,000. Both choose split, each get 5,000. One choose split, one steal. The person who chose steal gets 10,000. The one who was nice gets 0. And if both of them choose steal, they both get 0. Okay, very simple game. Again, very hard to guess what it is. So here's an example that we chose. So that's the final discussion that we're going to use, that they have each time before they make the decision. Guesses. What did each one do?
Both steal.
Both steal.
Yeah.
Anyone else?
Both steal.
You don't trust anyone today. You probably think that I'm lying to you as well. No other predictions? But that's good. The fact that you cannot predict, I think, is the main point. We just don't know how to predict what they're going to do. In this case, the guy steals, she splits. Like you said, I look you in the eye, and I look you in the eye, she said twice, and he chose to steal. So that's what we're going to use as input. Instead of the videos that we created before, we got videos of this game. And the videos contain lots of things, lots more than what we usually do, what we usually have. And I think that the most interesting aspect that we have over here is that you see the other person, you see the interaction, right? You see the people, and you see the discussion between them, and that's interesting. For the machine learning, we had, on top of that, we had this facial recognition, facial analysis software that looked at it. Now, we're talking about conditions that are very far from ideal for this software, right? Because we need to focus only when he talks or only when she talks, right? So each one is only at one person, not from an ideal angle. So it's definitely not what we would have done if we were interested in facial analysis. That's what we used, and I think that it's nice, and everything that we did over here is really the hardest way of doing it, and it still works, so I think it's nice. So the algorithm, the machine learning will get the analysis, the facial analysis. We'll do the magic, and all this other good stuff that will go into it, and at the end, will tell us what's the probability that this person, well, we'll talk about it in a second. At the end, we were able to get 430 videos for contestant. There are a bit more, but we couldn't get all the videos. You can see that it's a very high-stake decision, and we see that about 42% of them choose steal, the rest choose to be nice. Can people predict behavior? The answer will be no again. Each participant saw 20 videos just like we saw. For each one, they were asked to predict the probability, so not just whether someone lied or not, but, well, actually, let's talk about the one in which each of our participants had to guess whether the person in the video chose to steal or to split, and were paid for accuracy. And again, pre-registered, was done online. Question about the design of the experiment? No. The predictive model, again, I'm not going to give you too much details about it. The way you do it, you take, say, 60% of the videos, you run this machine learning magic, the algorithm, which is not that different from regression, but it's a regression that penalizes parameters that you put over there. And then you take your prediction and test it on out-of-sample videos, right, that you kept on the side. Tree-based, if you know what it is. Here are the results. Participants are really not good at this task, not surprising at this stage. We see that something like 53% of the people are good at it. We had two versions of the game. In one case, you did all the 20 without getting feedback. In the other case, you made, after each guess that you made, you were told whether it was true or false. Didn't make a difference. They were not better when they got feedback about whether they were right or wrong. Machine learning, we got it to 70% using really off-the-shelf, the most standard algorithm. Our goal over here is not to say that we created some kind of the best algorithm to detect lies. I'm sure that some people in this room can build a better model, a better algorithm, but it was just, that was enough for what we needed. Questions about this? No questions. That's just to show the graphics. So if the higher the probability that the video will be, so if the algorithm predicts that a video contains a steal decision with high probability, then that person actually steals with high probability, and the opposite for people, it's quite flat, as we saw before. Right, so people are not good at this task. Our algorithm is really good at this task. Our algorithm doesn't give us 0, 1, doesn't say whether the contestant chose to steal or split. The algorithm gives us some probability. So the algorithm can tell us that it predicts that with 75% chance, this person chose to steal. What we did in this one is basically using the 50% cutoff, right? So if the probability that the algorithm assigned to it was over 50%, we said that it chose to steal. If it was below 50%, we said that the algorithm predicted that he splits. Okay? Any questions about that? The next question that we have is, how can we learn from such machine learning, from algorithms like that? There is quite a large literature starting in the 80s, I think, maybe even a bit earlier, about algorithm aversion. People don't like to learn from algorithms, don't like the feedback of algorithms. And the question that we were interested in is, how can we actually make people use this kind of feedback? Right, so that was what we had. What we chose to test was flagging. So if the video tells us, if the algorithm tells us that this person chooses to steal with more than a threshold probability that we say, then we flag this video. And we want to see what's the impact of flagging, right? What is it going to happen? Is it going to influence them, increase predictive power, and so would people actually use this advice that they get? And we'll also give them opportunity to delegate it to the algorithm. So we'll have a treatment in which people can say, I don't need to watch the video. I'm going to follow the algorithm. Whatever the algorithm says, that's what we're going to do. Okay. Flag experiment. So the first one is one in which we just flag videos and people can choose whether to follow the predictions or not. So they watch 8 videos, and they watch 20 videos in this one, and for 2 of them, we flag them and say, the algorithm predicted that this person was very likely to lie. We didn't tell them that the threshold that we used was 70 and 30, but we did tell them that the algorithm said that this person is very likely to lie, or this person is very likely to split. Okay, so those were the flagging. You saw 4 videos with flags. We told them just that it's a machine learning that looks at the facial analysis and comes with prediction. We didn't tell them that the machine learning is better. We didn't give them the probabilities because, we just wanted to tell them that, I have the statement. I can show you the statement, what they saw actually. So we have used contestant facial expression and speech in the video to train a standard machine learning algorithm to predict when a contestant will choose split or steal. We use this algorithm to flag your videos for which the algorithm either predicted that the contestant chose to split with very high chances or very low. This flagging will be shown as a message that informs you that the algorithm made such prediction before you provide your guess. Okay, so nothing about the probabilities. I hope that you're convinced that people are not good at detecting lies, but the reason is not because there are no cues over there. The cues are out there. The algorithm can find them. For example, happier people are more likely to tell the truth, and there are many others, but we don't detect them, right? So that's, I think, an important point. So the algorithm is going to be better than us. The question is, how do people feel about it? I was not surprised that the algorithm is better, but many other people, the algorithm aversion literature basically says people will not believe the algorithm. Now, most of this, if not all of the algorithm aversion literature is before we had machine learning. So those were kind of models that were really primitive and were not that good. Right, so I think that now it's time to look at it. I think that one of the presentation in the morning discussed it, touched on it, right? Now is the time to actually look at algorithm aversion with machine learning to see what's going on. Okay, so what do we see over here? Effects of flags. So first of all, we have the control over here. Now it's important to understand that we had each video, so the person watched 20 videos, right? And even if the videos were the same, the videos for which the algorithm had very strong prediction sometimes were flagged, but sometimes were not flagged. Right? So now we can have also we can compare what happens when I see the video and I know that it's flagged, or I just see the video and I don't know that it's flagged. Right? So that's something that is useful. Over here we see the 3 cases that we have: no flag, very low steal, very high steal in the control, which means that they did not see that it's flagged. If they don't see the flagging, there's no statistical difference between them. Right? They're just, they are bad at all of them, all the cases, and they don't distinguish between them. That's what happens when we show them the flagging, right? So when they see the flagging, so if it says very low probability, they reduce the guess, right? So if before they saw the flagging, they thought that the probability of stealing is 40%, now they think that the probability is lower. And so basically they're following the recommendation, the flagging. So if they see that a video was flagged as very high chance of steal, they are much more likely to guess that the contestant actually chose to steal. Okay, so people do use this kind of flagging information. I don't think that I mentioned I was too excited to show you where is it now? The instructions. We also had a treatment in which the participant could choose to delegate their decision to the algorithm. Like I said, I mentioned it before, right? So I could choose to simply say, for the videos that the algorithm flags, I want the algorithm to make the decision. I don't need to see the video even. I'm just going to do whatever the algorithm says. And for these videos, what we see is that the people who chose not to delegate, they saw the flagging, they chose not to delegate, they were just as good as the people who saw the videos, the flagging. If you chose to delegate, almost by design, because the algorithm is right most of the time, you were much more likely to be right. Okay, so people are willing to delegate. We see the numbers over there. 54% of the participants chose to delegate. Now, I would choose for sure to delegate because I know how bad people are, and I don't think that I'm better than the average person in this. So I would choose to delegate. We see that about half of the people are willing to delegate, and they are, of course, more accurate in their prediction. It also affects accuracy in a similar way, but I don't want to talk about it. People have limited ability to predict behavior. We saw it before, even in this setting. Algorithms do better, not surprisingly. Simple flags can increase accuracy, and people are willing to delegate. So as a result, when we see flagging, people are actually better at guessing. Why should we care about this? So think about YouTube. Imagine that YouTube uses this kind of simple algorithm, right? So imagine that we can do this, and they can choose a higher threshold if they want, say 90%. And then they can flag these videos for two reasons. One of them could be, we want someone in the back room. So there are like 5 trillion, whatever, gazillion videos uploaded every minute. They cannot actually audit all of them. But if the algorithm will flag some of them, then they can have people look at them. Or maybe it's just for the end users. When I look at the video, they will not take away the video, but the algorithm would have over there, you know what, this one is probably true, and this one is probably false, right? So that could be something that is very useful to automate the decision which videos we should believe more and which we should believe less. I think that was my last slide. Yes.